we're gonna start off with the fun problem of the day again today while we wait for everyone else to come in. Okay, so for this problem, you'll need to use the divisibility rule for 3, which is something we'll go over. So, the divisibility rule just says that if the sum of the digits is a multiple of 3, that the number itself is a multiple of 3. And so the sum of the digits of this number is a plus b plus 19. And for this number, it's a plus b plus c plus 15. And now, you know that both of these are divisible by 3. So that means their difference is also divisible by 3, which means that c minus 4 is divisible by 3. And so this tells you that the possible values of c are 1, 4, and 7. Okay, now all of you who submitted the homework did well on it. And so now I'll just go over the problem that had the most errors. So for this problem, imagine the cuts going one at a time. The first cut, it obviously just removes the box of 2 by 2 by 3. Now, the second cut removes 2 boxes because you've already counted for the central cube. So you just need to account for these 2 boxes on opposite sides of the central cube. So that's 2 of 2 times 2 times 0.5. And the third cut does the same. So the volume of these cuts takes out 12 plus 4 plus 4 equals 20. So the volume of the remaining is 3 cubed minus 20 equals 7 cubic inches. Okay, so today's class is going to be number theory part 1. We're first going to lightly touch up again on Gauss sums. We already went over this during the algebra section of the class from a while back. Okay, and this is this. This is some more review, and here's a problem. Okay, instead of waiting for people to submit, I'll just directly go over this. So, this basically tells you 1 plus 3 plus 5 plus all the way to plus 2n minus 1. Sorry, I was paused share again. So, the, the first sentence basically, like all the information in the problem basically tells you that 1 plus 3 plus 5 plus all the way to 2n minus 1 equals 100, where there are n rows. And yeah. And now, so you can, so a well-known fact is that the sum of the first n positive odd integers, their sum is n squared. So n squared equals 100 and n equals 10. And if you want to know why that's true, you'd basically just use the same argument, a similar argument like this. Okay, and now here's the sum of the first n squares and the sum of the first n cubes, but you probably won't need this. Okay, now here's an example. So for this problem, first of all, note that there's a total of 5 hours between 10 a.m. and 3 a.m. Then you need to add another trip because that doesn't include one of the two endpoints. So there's a total of 6 trips. So the answer is 100 plus 99 plus dot 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 plus 95 equals 6 times 100 minus 1 plus 2 plus 3 plus 4 plus 5 equals 600 minus 15 equals 585 tourists. And now here's another easy example. Okay, so this problem is basically 1 minus 1 plus 1 minus 1 plus all the way to plus 1, and all of these cancel out. So the answer is just 1. Okay, so primes. So a prime number is a whole number greater than 1 that cannot be made by multiplying other whole numbers. So the first few primes are 2, 3, 5, 7, 11, 13, 17, 19, 23. And if you can make it by multiplying, if you can make a number by multiplying it with other numbers greater than 1, then it's composite. Okay, so factors are the numbers you multiply together to get to another number. And the prime factorization is finding which prime numbers multiply together to make the original number. So here's an example of using primes to solve problems. Okay, so the sum of three primes is even. This means that one of the primes is p, which means that you just want two primes that add to 98. So you can go from top down with the primes. They're 97, 83, 79, 73, etc. So their differences are 1, 9, 15, 19, and now here we can stop because 19 and 79 are both prime, so the largest possible value is 79. So a way to test if something is prime, there's no really good way. It's there's really mostly just this. Okay, now here's your next example. Okay, so we can prime factorize each individual component into this. And so when you write this out, it becomes, and this makes it clear that the only prime that has a double factor in this is 3. Now, Legendre's formula. Uh, okay, This is something that you really do not need to know. Okay, but this is Legendre's, which is fairly important. Okay, now here's your next example. Okay, so the number of zeros that appear at the end of a product equals the number of factors of 10 in the product. And a 10 is formed by the product of a 2 and a 5. And clearly, there's more factors of 2 in the 50 factorial than 5. So we just need to find the number of 5s in the prime factorization of 50 factorial. And this just equals 50 over 5 floor plus floor, 50 over 25 plus floor, 50 over 5 cubed, and so on. And these terms are all 0 because 50 is less than 5 cubed is less than 5 to the fourth, and so on. So it's 10 plus 2, which is 12. So 12 zeros appear at the end of 50 factorial. Okay, so divisibility rules. Let A and M be, and then this is a quotient and remainder. This is a theorem. Okay, now here's a list of divisibility rules. And there's no divisibility rule for 1 for obvious reasons. For 2, it's enough if the last digit is even. For 3, if the sum of the digits is divisible by 3. And this can be done by, okay, 4, if the last two digits are divisible by 4, because 4 is a factor of 100, so the digits past the hundredth digits don't matter. For 5, the last digit is 0 or 5. The divisibility rule for 7 is a lot stranger than most of the rest. You double the last digit, and then you subtract it from the number that remains when you took out the last digit. And the result must be divisible by 7 if the initial number was divisible by 7. 8. The last three digits are divisible by 8. And similarly to the 4 case, it's because 8 is a factor of 1000. So 9. The sum of the digits are divisible by 9. And you can prove this fact by using the fact that 9 plus 1 equals 10 and some of the divisibility property, distributive property. You can do the same. The proof is really similar for 3 because it works this way. Anyways, okay. 10. The number ends in 0. 11. The alternating sum is divisible by 11 if and only if the first number was divisible by 11. And you can prove this by using the fact that 11 minus 1 equals 10. Okay, now here's an exercise to practice those divisibility rules. Okay, so you know that QRS is divisible by 5, so S equals 5. And now, and you also know that R is even because QR is divisible by 4. So you also have that RST is divisible by 3, which means that R plus T equals 4 or 7 or 1, but 1 cannot be formed using the digits 1 through 5. So if it's 4, then R T equals 1, 3 in some order, and this cannot work because we already determined that R must be even. So R plus T equals 7, so R equals 2, and T equals 5. So now you know that QR is divisible by 4, so Q equals 2. Oh wait, sorry, not this. R equals 4, T equals 3, and so Q equals 2. And then this means that P is the only digit left, which is 1. Okay, now the number of divisors of a number. So 60 has a total of 8 divisors. 1 and 60, 2 and 30, 3 and 20, 4 and 15, and 6 and 10. Okay, now try this example. Okay, so I'll give a hint. So the prime factorization of this is 2 to the 4th times 3 to the 8th times 5. Uh, okay, so if it's the square of an integer, then the exponents must all be even. And that leaves 3 ways to choose the exponent of the 2, 5 ways to choose the exponent of the 3, and 1 way to choose the exponent of the 5. And so this gives you 15 square factors. But now it must be greater than 1. And one of these is 1, so the answer is 14. Okay, now to find the sum of the divisors of a number, you first compute the prime factorization of n and use exponents like this. Now, for each exponent, add up all of its powers that are less than or equal to that exponent. So, this is an example. And now, take the n products of all of the sums and multiply them together. And that's the sum of the divisors of n. Okay, now, this is just a numerical example. So, the sum of the divisors of 24, you can prime factorize 24 as 2 cubed times 3 to the first. And so the sum of the divisors is 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed times 3 to the 0 plus 3 to the 1 equals 15 times 4, which is 60. Okay, now try that again and for 360. Okay, so 360 equals 2 cubed times 3 squared times 5. So the sum of the divisors is 1 plus 2 plus 4 plus 8, 1 plus 3 plus 9 times 1 plus 5 equals 15 times 13 times 6 equals 1170. Okay, now some factoring techniques. So the difference of squares says that for any two numbers a and b, you have that a squared minus b squared equals a plus b times a minus b. And now try to use that in this next example. Only put stuff in the chat if you want to ask a question, want to only put stuff in the chat if it's like relevant in some way. Okay, I'll just give a hint. Okay, there's your hint. Okay, so continuing off of the hints. Okay, so the minus 2 squares cancel out, so you just get this, and this simplifies to 2 times 112 equals 224. So x equals square root of 224 plus 1 equals 15. And you don't need to worry about the negative because the problem says x is positive. Now, this is Simon's favorite factoring trick, and it can be used on equations that look like this, or somewhat in that form. You can find more about it using any of these two links, since I'm pretty sure these two are the same video. It's Simon because that's the name of the person who first made it popular. Okay, so some other factoring tricks are the difference of cubes, the sum of the cubes, and this is Sophie Germain. Okay, so here's another example. Okay, so for this problem, if you set n equals 1, then you have that m is less than or equal to n plus 1, which is clearly always true. So the answer is infinitely many m. Okay, now here's the first exercise. Okay, so for this problem, the elements of D are just the ones that are remainder of 5 when divided by 6. I'll just write it as 5 mod 6. You don't really you understand what that means right now, but basically it's just saying the numbers that leave a remainder of 5 when divided by 6. So the sum is just 5 plus 11 plus 17 plus all the way to plus 65. And this is just 70 times 11 over 2 equals 385 by using the sum of the terms in an arithmetic sequence formula. And here's your next exercise. Okay, so the primes must be of different parities, otherwise these won't all add up to the same. These the numbers on the backs and the one on the front won't add up all to the same number. And so 2 must go with 59. So the sum of the front and back numbers are 61. So the number on the back here is 17, and this one is 23, and their average is just 14. Okay, now here's your next example. The date isn't given for a reason. The date is not meant to be the date of the problem. This is just some random day and some random year that you can't figure out until after you solve the problem.
Can I use the bathroom?
Sure. Okay, so let the numbers on the uniforms be A, B, and C. So you have that A plus C is less than D, where D is the date, and A plus B greater than D, and B plus C equals D. So now all of these sums are less than equal to, oops, less than or equal to 31. So none are larger than 19. So they must be pairwise distinct. And so you can do some elimination because the three uniform numbers must be these. And after doing some elimination, the only case where this is good, everything works out, is this. So the uniform number of Caitlin is 11. And yes, the day of this problem, the date in question is not supposed to really be mentioned. And here's your next question. Sorry, I accidentally clicked a button. And just to clarify, n equals the number in question. Okay, so you cannot have B and D simultaneously true because the number is divisible by 7 and it's prime and it has only one even digits. But these two combined force the prime to be 7, and this is not true for 7. Erase. And so this is bad. Now, the same thing happens for C and D because all the primes between 10 and 20 do not have any even digits. So this is bad. So if D is true, then both B and C are bad. But you're given that three of them are true, and you've already ruled out two of them, which is bad, which means that the false statement is D and the rest are true. And so the only number divisible by 7 between 10 and 20 is 14. And it satisfies condition A, B, and C. And here's your next example. Oh, and by the way, the more of these exercises that you do in class, the less problems you have for homework. Okay, so a hint is that you can consider it by grouping the five. For example, 1 through 5, 6 through 10, and so on. The number that'll be added each time differs between each group, which is why you should divide them into groups of 5. Okay, so first of all, clearly the number of factors of 2 is going to be larger than the number of factors of 5, so it's the factors of 5 that matter again. So from okay, first of all, from n equals, okay, I'll erase this, n equals 5 to 9, you get plus 5. N equals 10 to 14, plus 10. And then so on. From n equals 25 to 29, you get plus 30. And this is 5 plus 10 plus 15 plus 20 plus 30 equals 80. Now n equals 29 plus, you get plus 7 each. So you need 3 numbers past 29. So the answer is n equals 32. Okay, this problem now. This shouldn't be too hard. Okay, I'll do some of the work for you. Here's the prime factorization. 2016 equals 2 to the 5th times 3 squared times 7. Okay, so th using this, there's 6 times 3 times 2 equals 36 divisors of 2016, but it's proper divisors. So 2016 itself doesn't count, so there's 35 of them. I'll skip this problem and save it for the homework later. Okay, this problem. Okay, so for this problem, it's basically just saying the number of students has 12 factors. And the smallest number that satisfies that is 2 squared times 3 times 5 equals 60. And conveniently, 15 is a factor of 60, and so is 6. Okay, this is probably going to be the final problem for today, and this should be 85. Okay, so this is an easy problem. So clearly, since this is odd, the primes are 2 and 83. If the 83 weren't prime, then this problem would be impossible. And the product is just 166. Okay, and that was the final exercise for today. So I guess class is over and you can stop the recording. And thank you for coming to class. Homework and the recording will be posted on Google Classroom either later today or tomorrow. And let's all thank my brother Gordon Chen for being my TA for this class again. And yeah, okay, you can leave now.
Bye.
Bye, everyone.
Bye.